to make my concrete with pebbles of exactly 1 inch, the best you can pack them is to a packing density of 74%, 26% would be voids. Now, let me ask you a question from based on what I talked to you yesterday. How much of cement paste do you want in your concrete? Roughly. What volume of cement paste do you want in your concrete? Or what volume of aggregates would you put in your concrete? 70 to 80% aggregate. So how much paste do you want in concrete? 15, remaining has to be base of 15 to 20% paste. If you do this best scenario, now this is assuming that you have placed them, picked them by hand one by one and have there's absolutely no other space left. How much space is left? 26%. You want to fill 26% of space and you want to have a good concrete with a lower water cement ratio, you will end up with a very high cement content will cause multiple problems, right? Heat of hydration, cracking, early cracking, shrinkage, lot of other issues, cost. So even with one particle, however well you choose one particle, you cannot make a good concrete. You have to have a gradation so that the larger particles get filled in by smaller particles. I'll show more of this in the afternoon. External closed pack structure is another structure that you have. So in theory, we can obtain a ordered pack of monodispersed particles, but in reality, it is often to get packing as shown above. Very small range ordered packing is what you want, especially if you talk about cement grains and other particles. Pack density and pore size just gives you whether you put in terms of pyramid, tetragons, hexagons, whatever, your maximum pack density for uniform size is going to be 7. So look at pore sizes, and this is another interesting idea. Entry pore area for a cubic is 0.21 A square, where A is the size of the cube. Tetrahedral 0.04 A square. Entry pore area over pi A square over 4 is 0.26. So if you look at all these numbers, void fractions 48 and 26. Radius ratio of primary sphere to interstitial states 1.34 to 4.4. We have a lot of these parameters of pore space that could be different. And why am I really worried about how my pore space looks? Why should I be worried about how my pore space looks? Is it for strength? For durability, right? How my pore space is organized is the only thing that dictates how chlorides and sulfates and moisture and all of these things go inside concrete. Period. You can tell me that I have only 10% porosity, but if the 10% porosity is really well connected, that is very high. You may have 20% porosity as a very big one hole in concrete inside, but outside is beautiful. Your durability will have no problem at all. So again, pure numbers will not tell you the whole story. Right? For pore structure and pore structure characterization, which we will discuss in terms of a few techniques maybe tomorrow. For pore structure, how the pore structure is organized is more important than how much of voids is there for durability. For strength, how much of total void is there is important. Right? Strength is inversely proportional to porosity. But for durability, it is the pore sizes that are much more influential. It's not just the porosity, pore sizes. Packing density and pore sizes are the same thing that I talked about. Random packing. So if I start to do, often packing density is 66.9%. In reality, particles are not very spherical, so that will also affect the packing density. So this is packing of particles of a log normal size distribution. If you have approximations, you can make it to ellipsoids, you can make it to polyhedrons, and you can make some approximations like that to do computer models. And then you can stack all those particles. If you have different facets, if you have spheres, random packing density, the sphericity of 1 is 0.6. But you see that there is some optimal value here for a certain sphericity. I mean, all of these are computationally calculated, but it's complicated stuff to discuss and deal with. Okay, size distributions, when we talk about plain cement, so we'll start with that. This is a fine Portland cement, probably a type 3 cement, which is high fineness. So D50 is about 9 microns. If I have 3 different sizes of limestones, I have a larger limestone and 2 smaller limestones. Yes, the same idea that I talked to you yesterday about tweaking the microstructure. If I do mixtures of different sizes particles, so this is a monomodal packing of large size, and this is what's called a furnace relation, where you can plot the packing density with the percentage of large particles. You see there's an optimal value, right? There's a certain optimal value that you can afford to have large particles. So the idea is that when I say large, it means the largest possible particle that you can use. Maybe your large force aggregates in certain size below which, and then you need to have a bunch of smaller particles forming that proportion so that you get the optimal packing density. So that is what you're looking at in mixed design most of the time to get an optimal packing density. And there is discrete packing, compressible packing model. We'll talk more about this in the afternoon. It's actually a good model for aggregates to do the maximum packing density for aggregates. So we figured out packing. Once we packed everything, all the particles together, you have pores, right? So you still have pores. That pore will be filled in concrete early on by